Right. Okay. Hi everyone. Welcome and thank you for attending our second Cygnas Solution Technology session, where we'll be focusing on machine learning. So my name is Sarah and I'll be the chair for today. I'm also the associate engineer for Cygnas Solutions. So on your screen right now, you should be able to see the agenda for today. We are honored to have two special guests today. I'll start off with an introduction to Cygnas Solutions and what we do, and then I'll introduce our two guests. We'll start off with Dr. Candice Cavendish, who is the CEO of CAE, who will provide an introduction to CAE's machine learning software. We'll then move on to Dr. Anil Vittal, who will walk us through some case studies, such as optimization for buckling and drilling, and even looking at a crash example for the front impact of a Toyota Yaris. These are just to name a few of the examples we have in store. We have a packed schedule today, so please, so I will be giving our speakers short warnings throughout. We'll also close out the seminar with a Q&A session. If you do have questions throughout the presentation, please feel free to type them out in the right-hand side in the Q&A box. We'll do our best to write replies as we go, but we do hope to answer most of the questions at the end. Even though they're not presenting today, the Managing Director of Cygnas Solutions, Hurm Kadir, and the Engineering Director, Ismail Jalisi, are also online to answer any questions you have about Cygnas Solutions and the work we do. So just an introduction to Cygnas Solutions now. So there we go. So Cygnas Solutions is based in Aberdeen, but we do have support resources available all across the UK and globally, where we aim to support and focus on three main areas, which are consultancy, software, and training. Cygnas is run by engineers with experience across a range of verticals, with specific focus in the aerospace and energy sectors. Our experienced engineers will support you with complex problems and technology adaptation with a view of making your company Industry 4.0 ready. Today, we'll get a chance to discuss more about a key enabler of Industry 4.0, which is machine learning and simulations. We're also proud to be authorized business partners with MSc Hexagon, where with their partnership, we aim to accelerate your company's development and growth. So this is what Cygnas Solutions aims to bring in all our advanced services, making sure it is always in accordance to the Hive collaboration values. The extensive experience in consultation and engineering analysis across a range of sectors allows us to strive for innovation and excellence in engineering. A key differentiator with us is that we can help with overcoming hurdles in implementing Industry 4.0. So if you were able to attend our inaugural technology session on Industry 4.0 a couple months ago, you might have already seen this wheel. Throughout these sessions, we try and focus on these technology sessions on an expert review of Industry 4.0 technologies ready for the energy and any emerging industries. This wheel essentially shows 9 elements, which we believe builds up to be Industry 4.0. So today's presentation will focus on machine learning and simulation. So on that note, I would like to reintroduce Dr. Candice to begin a discussion on machine learning.
Thank you, Sarah.
Yeah.
Okay, let me just put this on double screen. So I will probably switch to another PPT in a couple of minutes, but we will see how it goes. Now, just one small modification. Well, the company CAE is now acquired by Hexagon. So it was announced at the beginning that we will be talking about CAE. No, we will not be talking about CAE anymore, but we will be talking about ODYSSEE, which is the main product of the company which was called CAE, and now it is owned by Hexagon. Now, what is this ODYSSEE technology? We call it more or less a platform or a technology because it involves a few software. It's not just one. Now, essentially, we are talking about the technology which is some sort of midway between simulation, between classical simulation, finite elements, etc. System modeling, which is more or less a low fidelity and a low cost, very fast simulation technology, but of course it's more or less 0D or 1D, so it's limited in in some cases, but it shows you how the function, how a complicated system can function, while simulation shows you how a particular component of that system can work or will work in quite detail. And of course, we have now today the machine learning component, which is being added to the work, let's say, toolbox we have as engineers. And these are typically occupying today 50% of network discussions. Everybody's of course interested, enthusiastic in machine learning, but we still don't, we still don't know how to use it for engineering, and we hope that today you will see a little bit how it will be used, how it can be used, at least within this our scope of activity. We don't claim to solve all the problems, but those which are solvable with our solutions, we will show you, and Anil will show you later. Now, this is very much traditionally based on scripting, and it has small generalization, and scripting means customization. But what we want to do with ODYSSEE is to somehow simplify this aspect, that you don't need so much scripting, Python, etc. But you can have an engineering tool which you can work with your data, with your simulation models, and of course you can encapsulate everything you do in your system model. So via these techniques, we will encapsulate simulation models in system models. Now, compared to a typical market positioning, where we all know also that with respect to optimization solutions, because essentially the use of what we are doing is in optimization domain, anything which has to do with parametric, multidisciplinary, etc. Modeling. Well, traditional tools today actually go up along this axis, this diagonal. When you have models which become more and more complex, and which of course become more and more fragile, in the sense that robustness is lost, well, you are more or less, I would say there's a bottleneck today here in this region, which is related to the fact that response surface methods are limited in their multi-dimensional analysis, and direct finite element methods are too expensive. So we are in a more or less bottleneck here, and ODYSSEE positioning is actually starting the problem from the other side. So considering that volumes of data which are available can be exploited, probably to simplify a little bit formulation of the problem using all the techniques which are available, machine learning, artificial intelligence, data mining, but in particular reduced order modeling, which is a compression technique, very interesting for CAE and sensor data. So we will be combining all these in order to replace a typical process, as I said, bottleneck, with this particular ODYSSEE solution. Now, if you consider that we are typically, when we are doing engineering, we are faced with a decision which has to be made, which requires some output, some knowledge of how that system or process works. Well, this is dependent on the data, the process, on the data we fill into the process, and then the process brings us an answer and we take a decision. Now, it is this part of it which is consuming most of the CPU, most of the time. And it is also why we think that we should replace this part by some other model of the same physical problem, which probably does not have the same level of precision, but which has a higher performance level. This output is the result of a simulation or a measurement activity, typically, which has its again, I use the term bottleneck, which has its finite element model. It's a bottleneck, actually. Every time you want to change a dimension, you want to change even a small change to the model, you want to change properties of the model, or you want to change the loading, well, you have to solve a complete differential equation. Well, it is costly. So we think that by replacing this part with some new, I would say, solution, we may be able to improve a lot this process. So what we will do, we will try to relate directly the parameters, variables, unknowns of a system to the output of that system and use learning here. This ODYSSEE part uses various learning techniques instead of solving the equation. Now, once we do this, we can, of course, accelerate everything. Anything which is repetitive, anything which needs to be redone a few times, or like parametric studies, or even more like optimization, where you have to cycle around the same problem, you change the parameters, or anything which has to do with exogenous set of parameters, like boundary conditions, like stochastic analysis, like uncertainties, etc. Well, they will be extremely benefiting from this replacement of this part by a black box. Now, this means also that, well, we have to construct this black box at the beginning of the analysis, but the cost of it is low. So if I want to compare it to a direct usage of the solver, well, all surrogate methods use an initial set of runs to somehow create a surrogate model, and then they go down. Then their cost is much less. So this is also true with what ODYSSEE does. So in a sense, we are using surrogate models, but not the same type of surrogate models you were used to, like response surface models, like polynomial based, or any other type of response surface, but we are using a technique which is called reduced order modeling, which I don't know how much time we have, but
you've got 5 more minutes.
5 more minutes. Yeah. That means I don't have the time to explain to you how it works. Just take my word for it. It works. But I will show you one slide on that. Now, this also brings us very close to the topic of digital twins. Why it's not a fancy word? It's no more a fancy word. It's actually a process. It means that instead of doing simulation, then manufacturing, and then service real life, doing it in a separate process, we just consider that all this is one single process, and of course the flow of information must be permanent. This can be done if this design part, which is the bottleneck, can be accelerated and transformed into a real-time solution like the one I have here. So everybody can now exchange information. The moment you have a question here, immediately you get an answer out. So this is thanks to this reduced order modeling and the technique it actually employs. Now, just one slide if I have time, Sarah. So don't shout at me if I.
No, you have time. Don't worry.
Time. Okay. Just now I will be able. I will have to leave a little bit earlier. So I try to give some answers before they're even asked. Yeah. Now since we are using this reduced order modeling, it is actually a combination of a whole series of AI techniques, but also interpolation techniques. I won't go into detail, but the idea here is that we compress data. We compress a complete finite element model, where in a let's say in an equation-based or a differential equation-based modeling, you would actually use the straight line here, the red line, and its equation to do your predictions. Well, in a data-intensive or data-centered approach, we use these blue points. And the ROM technique is a technique which actually transforms those blue points into a reduced set of points, very little number of points, which are sufficient to explain what is happening. So instead of using all the data, we will use a few of them, and those are rich in information which allow us to to be predictive. Now this is based on a parametric form of the system. We extract that. We do transformations. These are done by eigenvalue computations and not by interpolations. But those are maths. Yeah, those are probably not relevant for you. It's just a projection. So you can. I will just go to. You can use somehow, instead of using all the available information, you can project them on a wall and use the information like we do in PCA. You do a PCA is principal component analysis. You can assess actually the behavior of the system by looking into maps like this. These are heat maps, and every point actually is a point which we had here. Every blue point can be projected into a heat map, and then we exploit this. Just a final word, you have seen this kind of solution in model analysis and some relevant solutions, so it's not completely unknown. It's maths, and well, it works. Just take our word for it.
Candice, you still have 2 minutes if you want to say any final thoughts or anything.
I still have 2 minutes.
Yeah.
Okay. So if I have 2 minutes, then I will say this. Now, reduced order modeling is a combination of two processes. One of them is what we call learning. Okay, that means we use decomposition techniques in order to project the data, project the know-how we have on the system on a new set of coordinates, which is much simpler. As you saw in my previous picture, I was projecting all the data of the system onto a 2D plane, and we do the analysis in that 2D plane. Now, once we are in that 2D plane, then we use classical prediction steps like interpolation, etc. This simply means, and by these two last pictures, I can stop. This simply means, let's assume I have a phenomena which is very complex to analyze. Here I have example of a flute. This is just the G4 note. So you see, even understanding how that varies in time is very complex, or in its variations. So if I wanted to have variations of this note, you will see I have to be able to fit functions like this, and no polynomial type function or any other function is able to do that. But the trick is known. The trick is in fast Fourier transform, for example, or Fourier transform. We know that instead of looking at the function in this complexity, it's enough to look at it in its frequency domain. Now, if we do that, same function which looks complicated here, for example, and which cannot be properly interpolated by existing response surface methods due to overfitting or due to the fact that time dimension cannot be properly integrated. Well, if we decompose it and project it on a new set of coordinate system, if you go from this thick blue representation of that phenomena into these thin blue representations of the same phenomena, but you see I have modes here. Instead of talking about the full component, I talk about the modes of behavior. Then everything becomes simple. And here, for example, a typical complex function. When I project it into that space, well, I have simple sine functions or cosine functions, and this is the trick with reduced order modeling. It recovers a complex system into simple forms of responses, and then we use combinations of those signals. So I will stop here and pass on the floor to Anil, who is, I think, somewhere. I have to find him which window he is. I have lost him. Here, okay. So please go on, Anil. I'll be listening to you.
Yeah, thank you, Candice, for condensing all that into a quick 15 minutes.
I am sweating now. Yeah,
I know.
It's hot. Yeah.
I know you do have to go. So, I mean, if anyone does have any questions.
Well, I'm here for another 20 minutes. I can stay for 20 minutes.
Of course you can. Please feel free to ask them now. You can always ask them in the end, and hopefully Anil will be able to help us there.
If I'm not able, we will get back. We can get back to them later. Like, and we can consult with Candice, and we can reply to them later.
But if all is good, I'll pass it over to Anil to discuss some case studies.
Yeah, thank you, Sarah. Thank you, Happy, for such an introduction. Yeah, we can't go in details because it's complicated mathematical expressions and things. But I will show you more application-wise where we are using. I got 6 examples with different CAE tool sets. We have done these use cases. I will take you through them if time permits. I don't know, maybe I can cover at least 5 of them, but let's see how it goes. So the first example I will take you through is an Adams drill. So basically Adams drill is a tool used for oil and gas industry to represent the drilling process. Simulate the drilling process. So this is basically the tool interface. Essentially, the tool is in an Excel format interface wise, not very complicated, very easy to use. And you can decide the whole process, you can do it within this interface. And we do have graphical and other animation capabilities with these tools as well. It's not like you just do everything, all the pre-processing and making your model in Excel and you can't visualize it. We do have visualizing capability, graphic capability as well in Adams drill. So the example what I'm going to take you through is a drilling problem where we want to see what will be the bending moment, twisting moment and axial load at 400 meter depth on a drilling exercise using Adams drill code. So for this study, as Campus explained, we need a set of input parameters which will represent your system, which you are describing your system using these parameters. For this example, I'm considering 3 of them. One is the RPM, other is the weight of the bit, weight on the bit WOB, and the rate of penetration. And I'm considering these ranges RPM is from 110 to 130, and weight is from 45,000 to 50,000 pounds, and the penetration is from 150 to 135 feet per hour. And with this information, I do have a tool in Lunar, the reduced order model or machine learning tool, which we used for this study is called Lunar. So Lunar can create your training data set or DOE set, we call it. And I'm using 10 sample points. We got different algorithms implemented in Lunar to capture this DOE, very good sample for your study. So whole results, the predictions and optimization depends on the samples you're selecting. So we have to select wisely these CAE sample points, and Lunar can help you in that as well. So once you have this training data, DOE sets, you have to run this in your preferred set of CAE tools, in this case Adams drill, which is also automated using a Python script. So Lunar gives the DOE training set, then it is each pre-processing input tag is created using Python script, as you can see on the right hand side. And then once you run it, we will measure this bending moment, twisting moment, and axial load as an output from the analysis. And once this data is fed into Lunar, Lunar learns from this data and data set using the capability, machine learning capability. So this is your training set, yes, the minimum number of training set, and it learns from that and do a prediction for a new data set which is not in your study. As I'm using, you can see on the left hand side down, my validation set, it's called XN in Lunar terms. I'm going to predict for 120 RPM, 50,000 pound weight, and 125 feet per hour penetration. And on this graph here, which represents the blue dots represents our actual CAE training data, and with respect to our training data, where our prediction point is in red, you can see that. So once the Lunar learns from this training, then you can predict, and it can predict for the new set. So left hand side, you can see here is our training data set. That's 10 individual, each line in this one represent individual CAE runs, and the results from individual CAE runs. I got 10 lines there, and on the right hand side, the blue line is the new prediction based on the new set of validation case, and I'm getting an accuracy of 94.4. Maybe if you see, like, I can improve this accuracy to as much as 98, 99% or above based on more number of DOE my training data around. So suppose, like, you're not getting a real good quality results what you are expecting, then you can increase the number of training data around this point here using the method available within Lunar. So there are different techniques available to improve your DOE set around the prediction area, and then you will get much better results. You can improve your results to a higher percentage accuracy. So you can see we are getting, for the bending and the twisting moments, we are getting really good prediction. So and for the axial load case as well, the accuracy of the prediction is 99.9 using cluster kriging method. So look at, like, you might be thinking Adams is always known, like, in its multi-body based simulation. It's really quick, but if you want to do a sensitivity study of these parameters, like I want to fix the RPM at 1, and I want to change the other 2 parameters in 100 times. I want to change, like, vary the range of that. I want to change the 100 combination in between those range and do it. It's a long time to do it, and using these techniques, using the reduced order model capability of Lunar, you can do it in seconds, rather than hours to do the whole scenario. So next example is also an oil and gas example. This work is actually done by our educational partner, Robert Gordon University School of Engineering, under Professor James and team. In this example, we are using the finite element capability and machine learning capability to optimize a design in a horizontal well. It's a horizontal pipe in a shale gas well to prevent the buckling, localized buckling. So you can see this is the problem definition. On the right hand side, you can see the well. This is how, like, you got the shale rock, and the oil is trapped in between different layers. So we have to capture the oil from these layers using cracks, yes. And how do we do the cracks? We do have localized explosions, as you can see the proponents here in the picture. That is localized exposure, explosion to initiate the crack, and further expanding the crack and increasing the crack size is using the hydraulic fracturing. And these are the factors, like, mainly contributing. And because of this hydraulic loading, we see a number of buckling cases, localized buckling cases due to this below mentioned cases, like, we got a weak fracture plane or weak bedding plane, then thermal loads and asymmetrical stress and other conditions, like, you can explain. And this is a serious issue as far as, like, oil and gas industry is concerned, because it costs loads of money for them. Suppose, like, in the range of 30 to 40 millions per US dollars, like, per well, it costs them to, with these problems. And we can see from the statistics on here, like, how severe the problem is around the world. So so this is an example of the real life deformation in the pipe. You can see on the left hand side, and we try to simulate that using the ANSYS tool. You might be thinking, like, this tool will support only MSC or hexagon products. No, the tool is agnostic. It can support any CAE product or any testing data, not only limited to CAE, it can support testing as well. The experimental data you have, we can use those data to do the reduced order modeling and machine learning and prediction based on that, or optimization based on that. So right hand side simulation using ANSYS shows the peak stress on the buckled stage 10 is around 773 megapascals. It's really reaching in the above the limits, and it's getting buckled locally. The finite element model we used for this is using ANSYS. You can see the 3D geometry and the FE model on the right hand side. Basically used a model with solid elements. We used around 149,000 elements for a 4 meters length of the well. And the material properties used for this study is shown below. And this is the transverse displacement we measured, like one of the characteristics we measured is the transverse displacement when it is getting buckled along the axial length of the pipe. So the idea, as I mentioned earlier, is to learn from a minimum set of data using the CAE capability simulation, FEA simulation, and then predict or optimize the system to prevent the buckling. So we want to modify the design in such a way that it won't buckle at all. If you want to do in a fully CAE environment, this will take thousands of runs. So instead of doing thousands of runs, do runs in hundreds, learn from that, then use the optimization methodology implemented in Lunar to do the prediction. So on left-hand side, you can see these are the parameters, the input parameters or the X parameters we call it, used to describe the system. There are 12 parameters and the lower bound and the maximum and the minimum range of these parameters. And we have used around 517 simulation scenarios or simulation data points in this one to determine the optimization. But we have used the option of clustering. In this study, we are not considering the whole set of 517 for the for prediction or the optimization. We are just using a subset of that using clustering and doing the prediction. So as you might already seen the methodology here. So we got an input parameter set which describes your system in finite element world or in a testing world, which could be mass, diameter, length, material properties, or anything like pressure, any loading condition, boundary condition, any data which describes the system. It goes into an input format into X file, which in a CSV format. And this is, and with that we will create the DOE set, the set to run the analysis. Then we got the output Y file responses, which we capture from the system. It could be force displacement or stress or strain or even deflection, deformation, you name it. Anything that you want to measure, acceleration, velocity, that will be your Y response, and that is fed into this ROM model or machine learning methods, and it learns from that, and then it can predict for a new set of variables, which is not within your, which is not part of the study. This is a new variable, and if you want to run these things, it will take ages in a complicated problem. Like you need HPC hardware requirement, higher HPC requirement, as well as the manual labor to prepare and run these simulations. So we can all replace this. Like we are learning from this is our minimum set. We are using a surrogate model. We are preparing a surrogate model with this information and using that surrogate model to do the prediction or optimization. So in this case, as I told, we are only using a part of this one. We only used 250 instances to do the parametric prediction, that is 50%. And in order to study optimization, we are just using like 129 instances, which is 25%. So this is the results, as you can see on the left-hand side. It shows like, from this selection of parameters, which cases buckled and which cases intact. And we want to optimize this like, for a minimum reduced stress as well as reduced deformation. We want to optimize this system. And right hand side, two graphs, you can see like we were doing the sensitivity study. We are changing, we are keeping all of the parameters constant, changing the slip displacement and seeing the effect on the stress value. The stress, the study, the curves in gray is our CAE training data, or the window we used to learn the physics. And the orange is the prediction using the scenario. again, for change in the case inner diameter, how the stresses will be varied. We have the study is shown in green. And we have used the optimization. There is an optimization capability tool within Lunar. We use a separate solver called Nova for this, which is embedded along with Lunar. So we can, as you know, we got classic DOE optimization techniques, as Campbell mentioned, response surface method and all, where you need, if you are using those methods to optimize it, you have to run number of hundreds of CAE runs to get better results. But here we are using really minimum set with the reduced order modeling capability. We are using really minimum number of set, not in 100, around hundreds or less than hundreds. We can for this kind of study. From next example, you can see I'm just using 10 or 20 sample points rather than hundreds. And we have optimized. So the blue color here is the optimized design variant by the Lunar, and the corresponding parameter is shown here. You can see one more thing, the capability of Lunar I want to mention. You can see the slider here. So these are all Lunar handles the time history files. It can and scalars, it doesn't matter time history or scalar. So you can, if you move the slider with respect to that point of the simulation or that point of engineering, simulation time, it can show you which parameters affects your simulation. So you can see the sensitivity of parameters, sometimes some parameters don't have any effect throughout the simulation at all, and you can remove it from your study. Or you can see which parameter contributes maximum at that point of time. So that capability is also there. Sensitivity parameter sensitivity study you can do in seconds, hundreds or thousands of runs you can do in seconds using this reduced order modeling capability. And if you want to do in terms of CAE, you have to do loads of CAE runs, expensive CAE runs. So once you do the optimization, if you click that plot, the optimized curve, it will give you the corresponding input parameters describing that curve. And then you can use that curve and rerun your analysis and see your simulation, your new design candidate is safe enough, or it's not failing at all. So that from the picture you can see on the left hand side, two of them two of them are failing at those locations, and after optimization you can see how safe your design is. So this happens in minutes, the optimization happens in minutes rather than hours or days in case of real-time CAE if you're using, or the old classical method of DOE techniques. So with this work, we showcased the multiple parameters or we can establish the relationship between multiple candidates, and we can optimize for a better design with a better safety factor. So we have reduced the von Mises stress in the pipe 87%, and the total deformation or the deflection we have reduced by 89%, and the factor of safety bumped up from 0.8 to 3.3. So these kind of capabilities, these kind of tools can enhance your engineering decision making and engineering capability in real time. So you don't have to wait, if you got a field issue, the input parameters for the field issue, or something happened, you don't have to wait and run the whole CAE process again, updating your parameters and all. You just come here, you just give those parameters and run and reduced order modeling prediction. You get the results in seconds. So the data is there, already there. Use those data, leverage that data, then do the prediction in seconds, and know the system behavior in seconds, and the design, how the design will change in seconds. So
I'll just let you know you've got 10 minutes left.
No problem. Thank you. So the next use case is an automotive use case. This is a frontal crash. Using LSDANA, this is again a different tool we are using here, not an MSE product. So it doesn't matter which tool you use. You can use these capabilities for any CAE or testing capability. So in this one, we are doing a frontal crash, full frontal crash. As you can see on the left-hand side, we use 3 parameters to describe the system: inner rail thickness in green, floor support structure thickness in yellow, and the velocity the velocity of the impact. We are changing that as well, and we are measuring as output response the driver seat acceleration, rigid wall force, and gravity at the COG location. And the system is like, we got around 378,000 elements to describe the system. And in an CAE environment, in an LS-DANA environment, this take around 3 hours to run per simulation. And total 17 DOE cases we consider, 17 sample points we considered for this run. As you can see on the left-hand side in the table, these are the 17 cases. And on the right-hand side on the scatter plot, you can see where these points are. And we are doing 3 predictions based on the table below on the left-hand side. And with respect to these, with respect to the sample point, where these predictions are, you can see that from the graph. So this is the actual validation of the 3, you can see, and we are getting really good prediction. So the lunar prediction is in thick line, and the FEM rerun with these predicted new variables is shown in the dotted lines. And you can see, like, the lunar is able to predict pretty accurate. One more capability of lunar is it can read. It got a parsing tool called Pulsar, which can read your ASCII files as well as the animation D3 plots or whatever. Like, and it can read that, process that files, and recreate the image without running LS-DANA or without running your CAE tool. So you can see in this one. You can see this is the animation, like, and the pink car is the lunar prediction of the simulation, and the blue is the LS-DANA, and it's really identical. So consider, like, spending 3 hours in a heavy HPC environment and running it in seconds using lunar. You can do lots of parametric study optimization of the system within, like, using with very minimum number of CAE runs. So this is another CFD example. So as you know, CFD simulations are pretty expensive in terms of HPC as well as the processing time. Simulation time, it takes lots of time. Like, if you have a heavy model, like a full car aerodynamic study or something, it will take, like, 4 to 5 days to complete the CFD analysis. On a 180 or like 200 CPU or 200 core HPC machine. So we are using the reduced order machine learning capability to predict the trajectory of trajectory of the canopy after the ejection using one of our CFD tool called SE Flow. So the total system have 173,000 elements, and each run takes around 4 hours to complete on an HPC machine 36 CPU. So this is what we want to do: learn from an initial base, like, well-selected CAE sample data, and do the prediction of the position of these canopy after the ejection in terms of displacement and Euler angle. So for this study, consider 2 input variables: ejection velocity ranging from 12 to 30 meter per second, and airspeed 51 to 77 meter per second. And on the right-hand side, you can see the DOE matrix we have used for the study, and 3 predictions we are doing at 3 points, as shown in green on the graph. So this is a learning curve, a learning data set we have used for the Y displacement. Each curve in this graph represent individual CAE runs based on the above 9 cases, the top table. And this is the simulation for that. After the ejection, what happens to the the canopy, the position, how it is moving. So when we consider the results, the Y displacements, the predicted lunar prediction is in thick curve, and the dotted curve is the validation against those predicted new variables using SE Flow. This is additional run. It's not the same run in CAE training data. It's the additional run and we are validating against that, and we are getting really good prediction. And Lunar is adaptable. Like, suppose if your prediction is not that great, you can add that prediction to your already existing CAE data and improve your prediction for the next run. So Z displacement and the gamma angle prediction, you can see from for all the 3 cases, we are really getting good correlation. So next one is a manufacturing example. We are simulating a self-piercing rivet case and doing a testing, actually the joint strength test using Simufact weld tool. So this is typically an example from aerospace or an automotive environment. As you know, like an automotive industry is now moving to lightweight BAW structure. They want to they want to use aluminum as a replacement for steel and make it lightweight. As all of you know, aluminum is weldability is very poor, and they use these kind of riveting technologies to bond the different panels. And it is mandatory, like, they have to prove the strength of these bonds and strength of the panel bonding using either physical testing or simulation. And in a typical car, suppose like in a Range Rover, there are a couple of hundreds of different material stack combination and 100, like around 100 of rivet die combination. And if you want to do the testing of these 2 combination, it runs into like around 23,000 combination. You have to test one by one. But OEMs don't do the whole 23,000 either physical testing or simulation. They select they pre-select a set of data from these 23,000 and it runs into 200 and even do 200 sets of physical testing or simulation, CAE simulation. It's a huge task for them in terms of labor intensive process and money involved and time involved. It's a big process for them to do it. And in this study, what we are doing,
we just have 2 minutes left, just because we have a few questions to answer at the end.
No problem. I'll finish with.
But
this.
yeah, you still have 2 minutes, so if you could just begin to wrap up, that'd be good.
Yeah, I'll finish with this example, I think. So what we want to do is take a small set of data, like we used 10 CAE training data for this for these variables. You can see on the top 4 variables we used to study the system, rivet type, dies, sheet thickness, sheet metal, sheet material. This can be this can be hundreds these parameters, but because it's a small study, proof of concept, we have used a very minimum number for this study. And this is actual simulation in for the riveting case, you can see, and the axial loading as well. What we measure is the shear force versus displacement of the joint. These are the 10 use cases, the CAE sample data we are using for the study. And this is one of the validation we have done for the above set, and you can see the lunar prediction in thick line and the Simufact validation in the dotted line, and we are getting really good correlation. So with minimum number of sets, like 10 sets, we are able to predict the performance of these joints. So with that, I will conclude. Sarah, I think.
Anil, I think it would be very useful for our guests to actually see. You remember we talked about the visual simulation as well.
That's
so I think just
one.
go over some of the examples. Just maybe don't go in detail, but just like introduction of what was done, and
right.
just go over the rest of them. Thank you.
I think this is the last one. Maybe I can do it in a few minutes, So the next one is another CFD example. This is very valid. This case is very valid at the pandemic time. We are in this example, we are using this CFD capability to measure the quality of air inside inside a restaurant, and what is the velocity profile of this air movement inside a restaurant. And with that, you can see where is the good quality air, where the circulation is really good, and where the quality of air is bad. We are not using any data as such, the text data. We are using images to do this study. It's not an image recognition capability. We do have image recognition capability, but we are using the heat map techniques to do that, and we are learning from that and converting that using entropy, or you call those techniques. So the tool used is SE Flow, and we got for this study, in order to predict the air quality, we got 12 sample points. These are taken different position of the air supply port at different locations, like along the length. You can see 12 samples points on the right hand side, and we are taking a cross section to predict the velocity, how how the air is flowing inside the restaurant. So we use 12 sample points for the air quality and 6 samples for the velocity prediction. So you can see, like these are the prediction we are doing on the air quality. We are taking 2 points, A and B. A is a point already in the CAE training data, and B is a new point which is not in the CAE training data. And you can see the cross section where we are measuring the velocity profile. So as the previous methods I explained, previous example cases I explained, normal procedure is you run CAE, your normal CAE activity, generate your data, then convert that into a Lunar readable format, that is in CSV format, text format, convert that into CSV format, feed that and do the reduced order modeling technique. Here we are actually converting your solver field files, like the ASCII files or whatever you call it, the plot files, into an H5 format, neutral for HDF5 format, and you are feeding that format into Lunar, and Lunar learns from that, like using the heat map option, or like measuring the color densities or quantities using RBG, like monitoring red, green, and blue and green concentrations, and do the prediction based on that. So once the prediction is, Lunar learns from H5, it do the prediction in H5 again, and you can read that H5 in your preferred post processor and do the post processing. You can actually visualize that, the Lunar prediction in your post processor. So this is an example for the air quality prediction at the location A and B. As I told, A is already a point already in this training data, and you can see left hand side SE stream simulation and the Lunar prediction on the right hand side. Both are identical. There is no difference, like and the prediction B, which is not there in the CAE training data, which is a new point, a new prediction point. You can see, like how good the prediction we get. We get a good prediction for that as well. This is the prediction using Lunar for the cross, the velocity profile along that cross section for 3 cases. You can see these are identical. You can't see, like no difference at all with the prediction. With the minimum, like 5 use cases, you are getting a really good prediction. You don't have to do like a number of more expensive CAE runs to get these kind of parametric studies. So that completes my presentation. Thanks for attending, and if you have any questions, please ask now. Or else, like if you want to go in details and discuss your problem, you got some problems you want to solve, and you can see this will benefit to solve. Please let us know. Please get in touch with the Cygnas, and then we can take it, like consider your problem one by one personally. Yeah. Thanks, Sarah, and thanks, Huron. Thanks for attending. Over to you.
Thank you very much for that. Give me one. Herm, can you read the questions if you don't mind?
Yeah, I'll do that.
Just can't get...
First question is, based on the validation data, can Lunar suggest a representative DOE?
Yes. Lunar DOE capability can suggest, like yes. It got the full capability to create. So I'm the whole prediction depending on the quality of the data. And what I do is, using the Lunar DOE capability, I create a sample point for like large number, like 100 sample points. Then I reduce that to my required level, like maybe 9 or 10 or 15 cases. So that in that voice, Lunar helps you to get a decent quality of data set for your prediction.
Brilliant. Next question is, it's related to the canopy one.
Yeah.
Are those new set of airspeed outside the boundary of DOE? So remember we discussed where, if, for example, if there's a point which is outside the DOE, is it actually predictive in that sense? Can you use it? And obviously in some cases, what's the accuracy, and does it vary?
You consider most of this machine learning or neural network, or you call all these technologies, they are only good interpolating results. They are not like, you can't, we do have other tools we can do extrapolations, not Lunar. Lunar can do it, but with other tools like Quasar and scripting, like, we can do the extrapolation. And depending on the quality of the data, we can get, you will get the results based on that. But these tools are purely interpolation. So between your minimum and the maximum data set, you can predict anything in between. Yeah.
Brilliant. So not that many, if there are any more questions, you can again put them and we can discuss them there. But I think, Anil, thank you very much for your time. We still have a couple of minutes.
Yeah.
Maybe, if you want to like to share maybe something else. I think there was one interesting example of the X-rays that we once saw of visual processing.
Let me get it.
And I thank you also Mr. Kevin Tash, who was very kind to take his time today for us.
Thank you, Khurram, who is the Managing Director for Cygnas Solution, for taking over the questions. I was having an issue with Teams, and for producing this live presentation. I mean, hopefully these case studies that Anil so kindly showed you how using machine learning we can avoid this long, complex, costly simulations, essentially maximizing your profitability by doing real-time predictive models and optimization. I think Anil's trying to find another case study looking at X-rays.
Yeah, this is a new capability, this is a new tool, like in customization of the CADLM ODYSSEE platform. This is done using the image recognition capability. Actually, what we are doing here is the same thing. You can do it in Lunar or other ODYSSEE tools. We can do the same kind of prediction as well. But we have created another vertical just to do the processing using the images and the animations or CAD data, or like you name it, any 3D components, like we can use this tool to do the predictions based on that. Especially for the health industry, what we are trying to create is we are trying to create a vertical where you like in a health industry, you might have number of MRI scans or X-rays, or like you get to do the prediction of conditions of your lungs, or you name it. So if you have such kind of data, then you can use that database as in training data. And Lunar or the machine learning capability of AI can learn from that database and help you to predict the condition of your system, like lungs, like if it is infected, or if it is good quality, like if it is good, you are healthy. It can do that kind of prediction using image recognition. When you consider the engineering aspect here, in this one, we are feeding the images of different tire tread patterns. So this one, actually, sorry, can you see my screen now?
Yeah, now we can see. So
yeah, this is the example I was talking about. This the health industry vertical, like we are developing. Tool is called AI. It is a simple form of artificial intelligence, or what we call it, AI somehow. But we are using the image recognition capability, as I explained earlier. this example, engineering example, we are feeding.
Sorry, I don't need to. It's just we've hit 11, so I do want to thank the people that could only stay for the hour. We will still be continuing for a few more minutes if you do have more questions, and we're just going to continue on with the presentation. But I'd like to thank the
This
people
is the
that,
last slide, Sarah. Finish.
No, don't worry, you can take your time.
So I got 6 examples, like 8 cases, 8 different shapes of thread pattern, and I'm using that thread pattern, defining what is the actual noise created by those thread patterns. We used our tool called Actron, MSC tool called Actron, and you can see the resonance, like the noise level predicted, and this is fed as the database into the AI as image and these curves, and it's learning from that, and then we are feeding a new case. This is our new thread pattern, and we are getting a good prediction based on that. Like, and you can see there is no difference at all in prediction as well as the validation using Actron. So we got image recognition capability within Luna or within our set of tools. Not only limited to images, animations we can use, or we can use, as I showed earlier, in the velocity case, it's an animation, or you can use the 3D CAD data, any data like all 3D representation we can use and learn from that, and do the prediction based on that as well. So thanks.
Perfect. So let's just go over last 2-3 questions that we can quickly answer, and then that will be the end of our presentation. Yeah. So one question is, hence all machine learning techniques are bounded within that's done. How different is machine learning prediction from statistical modeling? What coding language is used in the software? So I think for the statistical modeling, you have obviously a number of visualization that you do, I guess, is different. If you have many number of variables which CAD-LM can handle, it becomes a bit more easier to visualize. Is that correct?
That's right. Yes. This is again like if you see the theoretical background behind, we are using all these methods, yes, statistical methods, and all those things behind our GUI. I think I won't be able to explain in that detail about this background, but Campus is the right person to answer that.
Perfect. So we can always send, you can send us those questions in the email. The last one, what coding language is used in the software?
Coding is a new, it's not Python, it's called Quasar. It's very similar to Python. And there are, if you want to learn, there are training materials, like all available, like, for this Quasar language.
One thing I would like to add here that Mr. Cavendish was working in Cranfield University for many years as head of department in crash dynamics, and this is where this has been many years in development and improvement of the whole system.
I think the history is like Campus was the director of the crash center, the Cranfield Impact Center, and he developed these tools for support the local Formula One industry.
Brilliant.
So that is the starting point for these tools.
Okay, everyone, thank you. I think this brings us to the end of this live event, and feel free to send us questions. You have the email address there. We all of us are would be more than glad to help you answer your questions and how which tools would be the best for your organization and how it can help you solve your problems. Thank you very much. It's been a pleasure having you all on board. Thank you.
Thank you.
Bye-bye.
Thank you. Bye.